Welcome, Math 252. We're looking at problem 21 from section 6.1 of the Hughes-Hallett text. In this problem, we've been given the graph of little f, which is the derivative of capital F of x, and we're asked to find the critical points of capital F. We're supposed to figure out which of those critical points are local maxima, which are local minima, and which are neither. And we're supposed to sketch a possible graph of f. So I'm going to start by collecting some information that this graph of the derivative, that this graph of little f gives me. And so I've redrawn the graph here so we can both be looking at it. And I'm going to look to see where little f is positive and where little f is negative, because that information is going to tell me where capital F, the antiderivative of little f, is increasing and where it's decreasing. So we can see, for instance, that from 0 to 1, little f is negative, so capital F must be decreasing. Keep in mind that little f is the derivative of capital F, and where the derivative is negative, the function itself must be decreasing. From 1 to 3, you can see that little f is positive, so capital F must be increasing. And then from 3 to 4, you can see little f is negative, so capital F must be decreasing again. We can also look at the derivative, little f, and find out about the concavity of capital F. And we can do that by looking to see where little f is increasing and where it's decreasing. So for instance, from 0 to 2, little f is increasing, which tells us in that same region capital F must be concave up. And from 2 to 4, little f is decreasing, so capital F is concave down. Now, capital F has critical points wherever its derivative, little f, is equal to 0. And you can look at the graph and see that's when x is equal to 1, and again when x is equal to 3. Now, you have a local extrema for capital F at a critical point if the derivative, little f, changes sign at that point. If you look at these two critical points we just found at 1 and 3, you can see that little f does indeed change sign at both of those points. So both of these points must be a local extrema of some kind or another. At x equal 1, we have a local minimum because capital F, we've just decided, must be concave up at x equal 1. And if it's concave up and we've got a critical point, then we must be looking at a place where we have a local min. Similarly, at x equals 3, we have to have a local max since f is concave, capital F is concave down at x equals 3. So now we're going to take that information, put it together, and get ourselves a graph. So I've condensed the information we had a second ago here, so it's in front of us. We know where our function capital F is decreasing, we know where it's increasing, we know where it's concave up, we know where it's concave down, and we know where to find a local max and a local min. What we don't have is information about how high or low it is. We haven't been given a function value for capital F, so there's lots of pictures I can draw here that are a possible graph for capital F. I've drawn one. You can see that we've got a function drawn for capital F that's decreasing from 0 to 1, has a local minimum at x equal 1, then goes back to increasing from 1 to 3, has a local max at x equals 3, and goes back to decreasing from 3 to 4. And you can also see that from 0 to 2 it's concave up, and from 2 to 4 it's concave down. So this is a good candidate for a graph of capital F. Any version of this graph, shifted up or down, would all similarly be a good candidate for the same thing.